In a previous segment, we talked about how to solve modular linear equations. In this segment, we're going to talk about how to solve modular quadratic equations, and more generally, we're going to look at how to compute modular eth roots. So as I said, now we know how to solve linear equations simply by using an inversion algorithm to compute A inverse and then multiplying the result by minus b. So the question is, what about higher degree polynomials? And in particular, we're interested in solving polynomials modulo primes, so solving polynomials in ZP, but polynomials particularly of the form x squared minus c, or y cubed minus c, or z to the 37 minus c, all in ZP. So solving this polynomial, for example, involves computing the square root of c. Solving this polynomial involves computing the cube root of c. Solving this polynomial involves computing the 37th root of c, and so on. So again, let's fix a primes p, and let's say that c is some element in ZP. We'll say that x in ZP that satisfies x to the e is equal to c, we'll call such an x the modular eth root of c. So let's look at an example. We say that the cube root of 7 in Z11 is equal to 6 because 6 cubed is equal to 216, which happens to be 7 modulo 11. And therefore, the cube root of 7 modulo 11 is equal to 6. So let me ask you, what is the square root of 3 in Z11? So the answer is 5, because 5 squared is equal to 25, which is 3 modulo 11. And similarly, let me ask you, what is the cube root of 1 modulo 11? Well, the cube root of 1 is simply 1, because 1 cubed is equal to 1 in Z11. In fact, that's true in modulo any prime. One thing I'd like to point out is that these eth roots don't always exist. For example, if I asked you to compute the square root of 2 modulo 11, you'd have a problem because the square root of 2 simply doesn't exist modulo 11. So now that we understand what an eth root is, the next question is, when do these eth roots exist? And when we know that they do exist, can we actually compute them efficiently? So let's start with the easy case. The easy case is when we want to compute an eth root of something, and it so happens that e is relatively prime to p minus 1. In this case, c to the 1 over e always exists, and there's a very easy algorithm to actually compute the eth root of c in ZP. So let's see how this works. So first, since e is relatively prime to p minus 1, we know that e has an inverse modulo p minus 1. So let's compute this inverse, and let's call it d. So let's let d be the inverse of e modulo p minus 1. Then I claim that in fact c to the 1 over e is simply c to the d modulo p. So if this equation holds, then first of all, it proves that for all c in ZP star, the eth root of c actually exists. And moreover, it gives a very efficient algorithm to compute this eth root of c simply by computing the inverse of e modulo p minus 1 and then raising c to the power of that inverse. Okay, so we kill two birds in one stone. So let's see why this equation holds. So first of all, the fact that d times e is equal to 1 mod p minus 1, what that means is there exists some integer k such that if I look at d times e, that's basically going to be k times p minus 1 plus 1. That's basically what it means that d times e is equal to 1 modulo p minus 1. But now what does that mean? Well, so now we can actually confirm that c to the d is an eth root of c. Well, how do we confirm that? Well, let's take c to the d and raise it to the power of e. If in fact c to the d is an eth root of c, then when we raise it to the power of e, we're supposed to get c back. So let's see why that's true. Well, that's simply equal to c times d to the e. And c times d to the e, well, by definition, is equal to c to the power of k times p minus 1 plus 1. Well, using the laws of exponentiation, we can write this as c to the power of p minus 1 to the power of k times c. All I did is I distributed the exponentiation using the standard laws of exponentiation. Now, what do we know about c to the p minus 1? Since c lives in ZP star, by Fermat's theorem, we know that c to the p minus 1 is equal to 1 in ZP. 1 to the k is also equal to 1. And as a result, this is simply equal to c in ZP, which is exactly what we needed to prove that c to the d is an eth root of c. Okay, so this is what I call the easy case. In fact, the eth root always exists when e is relatively prime to p minus 1, and it's very easy to compute it simply by using this formula here. Now let's turn to the less easy case. So the less easy case is when e is not relatively prime to p minus 1, and the canonical example here is when e is equal to 2. So now suppose we want to compute square roots of c in Zp. So if p is an odd prime, and in fact we're going to focus on odd primes from now on, then in fact p minus 1 is going to be even, which means that 2 divides p minus 1, and indeed the GCD of 2 and p minus 1 is not equal to 1. So this is not the easy case. So the algorithm that we just saw on the previous slide is not going to work when we want to compute square roots modulo an odd prime. So when we work modulo an odd prime, the squaring function is actually a 2-to-1 function. Namely, it maps x and minus x to the same value. It maps both of them to x squared. And as a result, we say that this function is a 2-to-1 function. So here's a simple example. Let's look at what happens when we compute squares modulo 11. So you can see that 1 and minus 1 modulo 11 both map to 1. 2 and minus 2 both map to 4. 3 and minus 3 both map to 9, and so on and so forth. So you can see that it's a 2-to-1 map. So in fact, these elements here, 1, 4, 9, 5, 3, all are going to have square roots. For example, the square root of 4 is simply going to be 2 and 9. And I claim that in fact none of the other elements of Z11 star are going to have a square root. And that motivates this definition to say that an element x in Zp we're going to say is called a quadratic residue if in fact it has a square root in Zp. Okay, and if it doesn't have a square root, we'll say that it's a non-quadratic residue. So for example, modulo 11, 4 is going to be a quadratic residue, 9 is going to be a quadratic residue, 5 is a quadratic residue, 3 is a quadratic residue, and of course 1 is a quadratic residue. So let me ask you, if p is an odd prime, what do you think is the number of quadratic residues in Zp? And I'll give you a hint, the squaring function is a 2-to-1 map, which means that half the elements in Zp can't have a pre-image under this map. So the number of quadratic residues is simply p minus 1 over 2 plus 1, and the reason that's true is because we know that exactly half the elements in Zp star are going to be quadratic residues because of the fact that the squaring function is a 2-to-1 map. So there can be at most p minus 1 over 2 elements in the image of that map. So half the elements in Zp star are quadratic residues. And then in Zp there's also 0. We also have to account for 0. 0 is always a quadratic residue because 0 squared is equal to 0. So overall we get p minus 1 over 2 quadratic residues in Zp star plus 1, the 0 element, which is a quadratic residue in Zp. So overall in Zp there are p minus 1 over 2 plus 1 quadratic residues. Okay, so the main point to remember is that roughly half the elements have a square root and the other half does not have a square root. I want to emphasize that this is very different from the easy case where e was relatively prime to p minus 1. If you remember, in the easy case, every element in Zp star had an eth root. When e is not relatively prime to p minus 1, that's no longer the case, and in particular in the case of e equals 2, only half the elements in Zp star have a square root. Well, so the natural question then is, can we, given an element x in Zp star, can we tell whether it has a square root or not? So Euler did some important work on that too, and in fact he came up with a very clean criteria to test exactly which elements are quadratic residues and which are not. And in particular he said that x in Zp star is a quadratic residue if and only if x to the power of p minus 1 over 2 is equal to 1 modulo p. Okay, very, very elegant and very simple condition. Let's see a simple example in Z11, so when we work mod 11. So here I computed the fifth power of all the elements in 11 for you, and you can see that this symbol, this x to the p minus 1 over 2, is always either 1 or minus 1, and it's 1 precisely at the quadratic residues. So 1, 3, 4, 5, and 9. Okay, those are the quadratic residues, and the other elements are not quadratic residues here. I'll circle them in green. These are the elements that do not have a square root when we work modulo 11. One thing I'd like to point out is, in fact, if we take an x that's not equal to 0, and we look at x to the p minus 1 over 2, well, we can write that as the square root of x to the p minus 1, right? The kind of the half bubbles out, and this is simply the square root of x to the p minus 1. Well, x to the p minus 1 by Fermat's theorem is 1, so x to the p minus 1 over 2 is simply a square root of 1, which must be 1 or minus 1. So what this proves is that really this exponentiation here must output 1 or minus 1, and we actually saw that happening here. It outputs 1 when x is a quadratic residue, and it outputs minus 1 when x is not a quadratic residue. This is not a particularly difficult proof, but I'm not going to show it to you here. It's in the reference that I point to at the end of the module. And just for completeness, I'll mention that this value, x to the p minus 1 over 2, has a name. It's called the Legendre symbol of x over p. And as we said, there's 4 elements in ZP star. This symbol is either 1 or minus 1, depending on the quadratic residuosity of x. Now, the sad thing about Euler's theorem is that it's not constructive. Even though it's a very, very cute theorem, it tells us exactly which elements are quadratic residues and which aren't. This theorem doesn't do it constructively in the sense that if we want to compute the square root of a quadratic residue, the theorem doesn't actually tell us how to do that. And in fact, even if you look at the proof is by an existential argument. So it proves that the square root exists, but it doesn't show us how to compute the square root when we want it. So the next question is then, how do we compute square roots modulo primes? So it turns out that's actually not so hard, and again it breaks up into 2 cases. The first case is when p is equal to 3 modulo 4, in which case it's really easy to compute the square root, and I'll just tell you there's a simple formula. The square root of c in this case is simply c to the power of p plus 1 over 4. You notice that because p is equal to 3 modulo 4, p plus 1 is necessarily p plus 1 is equal to 0 modulo 4, which means that p plus 1 is divisible by 4, and therefore p plus 1 over 4 is an integer. And that's exactly what allows us to compute this exponentiation, and I claim that that actually gives us the square root of c. Very simple formula that directly gives us the square root of c. So let's verify that that's actually true. Well, I'll take c to the power of p plus 1 over 4 and square that. And if in fact, if c to the p plus 1 over 4 is the square root of c, when I square it, I should get c. So let's see what happens. So first of all, by laws of exponentiation, this is simply equal to c to the power of p plus 1 over 2. And that I can write as c to the power of p minus 1 over 2 times c. Okay, again, this is basically, I took 1/2 and moved it out of the exponentiation. Now, what do we know about c to the power of p minus 1 over 2? Since c is a quadratic residue, we know that c to the power of p minus 1 over 2 is 1. And therefore, this is really equal to 1 times c, which is c in ZP as we wanted to show. Okay, so this basically proves that c to the power of p plus 1 over 4 is the square root of c, at least in the case when p is equal to 3 mod 4. Now you should ask me, well, what about the case when p is equal to 1 mod 4? In that case, this formula doesn't even make sense, because p plus 1 over 4, this exponent here, p plus 1 over 4, is going to be a rational fraction, and I don't know how to raise c to the power of a rational fraction. Nevertheless, it turns out that even in the case when p is equal to 1 mod 4, we can efficiently find square roots, although it's a little bit harder. And in particular, we don't have a deterministic algorithm to do it. We have to use a randomized algorithm to do it. But this randomized algorithm will actually find the square root of x mod p very efficiently. I guess I should mention that if someone could prove that the extended Riemann hypothesis, this is some deep hypothesis in analytic number theory, if someone can prove that that hypothesis is true, in fact, it would give a deterministic algorithm for computing square roots even when p is equal to 1 modulo 4. So the reason I like to mention that is because you notice that as soon as you put the computational lens on something, for example, I ask you to compute the square roots of a number x modulo p, coming up with an algorithm already requires extremely, extremely deep results in mathematics, some of which are not even known to be true today. So as things stand today, we simply don't have a deterministic algorithm to compute square roots where p is 1 mod 4, but as I said, we have good randomized algorithms, and this problem is considered easy. Essentially, it boils down to a few exponentiations, and as a result, as we'll see, the running time of computing square roots essentially is cubic in the number of bits of p. So excellent. So now we know how to compute square roots mod p, and so now we can talk about solving quadratic equations modulo p. So suppose I give you a quadratic equation, and I ask you to find a solution of this quadratic equation in ZP. Well, so now I claim that you know how to solve it. The way you would solve it is basically you would use the high school formula for solving quadratic equations. So the solution is minus b plus minus square root of b squared minus 4ac over 2a. And I claim that you know how to compute all the elements in this formula. So you know how to compute the inverse of 2a, so you can divide by 2a. That's done using the extended Euclidean algorithm. And we know how to compute the square root of b squared minus 4ac using one of the square root algorithms from the previous slide. And of course, the formula will only be solvable if the square root actually exists in ZP. So that's cool. So now you guys know how to solve quadratic equations in ZP. So now the next obvious question is, what about computing ETH roots modulo composites rather than modulo primes? So we can ask exactly the same questions that we asked before. So when does the ETH roots modulo n exist? And if we know that it exists, can we actually compute it efficiently? And here the problem is much, much, much harder. And in fact, it turns out that for all we know, computing ETH roots modulo composites is as hard as factoring that composite. Now for a general E, this is actually not known to be true, but the best algorithm that we have for computing ETH roots modulo n requires us to factor the modulus. And once we factor the modulus, then it's actually easy to compute ETH roots modulo each of the prime factors, and we can combine all the ETH roots together to get an ETH roots modulo the composite n. So it's a very interesting case where computing ETH roots modulo a prime was very easy. In fact, for many E's it was very easy, but computing ETH roots modulo composites is much, much, much harder, and in fact requires the factorization of n. So that's all I wanted to tell you about ETH roots. In the next segment, we're going to turn to modular algorithms, and we're going to talk about addition and multiplication and exponentiation algorithms, modulo primes and composites.